Okay, so in today's lecture, we are going to look at a brief summary of all the MOSFET amplifier-based designs that you have looked into in the past. So this is kind of like a cheat sheet that you can use for future references that, okay, what kind of MOSFET amplifiers are there and how to analyze each of those different designs for the MOSFET amplifiers. That is something you can refer to in this cheat sheet. Okay, we'll also look into some analog IC building blocks now that we understand how MOSFET amplifiers work. And then gradually we'll start looking into differential amplifiers as well. So that's what we're going to do in today's lecture. And we'll continue our discussions on differential amplifiers for the next 2 lectures or so. At the same time, your homework number 6 has been uploaded, which will be due next week, in a week or so. And it has, I'll probably also show what this has as. So it basically has this common source type amplifier once again. So you're applying your input to the gate, and you have a bias at your source. So you have this bias current at your source, but what you need to find out is the small signal input impedance Zin. That's the input impedance seen at this node. But for the transistor M1, you can use the small signal model as mentioned over here. So the only difference from what you have learned in the past is that in the past, whenever you looked into the small signal model of the amplifier, you assume that the gate to source terminal is open, right? So you apply a voltage source at the gate. The source terminal is grounded, AC ground, which is true in this case as well. And you have a GM-VGS amount of current flowing from gate to source. But here the difference is that you have a capacitance between the gate and source terminal. So this will give you some idea about what you can expect if you take a RF circuit design. So in radio frequencies, whatever amount of parasitic capacitance is present between, let's say, any 2 terminals of the MOSFET, that becomes important. And we haven't looked into this in detail in this course, but this is just to give you a glimpse of what can come if you're taking a RFIC design course, where all the capacitances are important. So there could be many different capacitances between the gate and source terminal. There could be a capacitance between gate and drain. There could be a capacitance between drain and source, and so on. So what this problem asks you is that if you have a capacitance between gate and source terminal, if that capacitance is important, how would your input impedance change? Because ideally you'll say that the input impedance is infinite. There cannot be any current flow inside the gate of the MOSFET. But because between gate and source you have a capacitance, you'll see that there could be some amount of AC current flow through that capacitance. So the current does not go into the gate of the MOSFET, but the current flows between the capacitance that is connected between gate and source. And that capacitance, again, is not a physical capacitance. It's a parasitic capacitance that exists between any terminals of any device. It's just that we didn't consider it because we wanted to make our life simpler till now. But this exists in any kind of circuit. So whatever circuit you design, this capacitance will exist between any 2 terminals. Now, of course, if you are working with enough low frequencies, you know that the impedance of a capacitor is 1 upon j omega c. And at low frequencies, that 1 upon j omega c is very, very high because omega is small. Now, if that is the case, at low frequencies, it is okay to ignore that capacitance. But in high frequencies, you have to consider the effect of that capacitance eventually. And that's the reason why I wanted to make sure that we have a homework where you get to know that, okay, there are these capacitances, and there is some effect of those capacitances when you calculate Zin, when you calculate gain, and so on. So right now, you do not need to consider or calculate gain or anything. You just need to find out the small signal input impedance, which ideally should have been infinite, but now it will not be infinite because of this capacitance that exists between gate and source. So you'll still apply the same method that you have learned to find out input impedance or output impedance of any circuit. It's just finding out the Thevenin equivalent resistance or Thevenin equivalent impedance at one port of the system, right? So you'll still use the same approach. The approach is nothing different. It's just that you'll get an idea that why this capacitor is important and how it reduces your input impedance from a value which is close to infinite to something that is finite. So that's what you learn from this particular homework. The second part of the homework actually has a little bit more complex circuit than what you have learned before. But what I will do in the next lecture, I'll not do it today, Today is just for you to go over this particular structure and trying to understand that what it means to have these multiple stages in the design. So, for example, here the first stage is a common gate stage. As you know, that input is applied at the source, the output is taken from the drain, and the gate terminal is connected to your AC ground. So this is the common gate stage. The output of the common gate stage goes to a common source, goes to a source follower over here, because the output is taken at the source, and it also goes over here, which is again a common gate stage. And the output of this common gate and the output of this source follower, both of them goes to these common source stage at the final output. So it's a much more complex circuit than what you have seen till now, but I have also provided a reference material to solve this problem in homework 6. Of course, the values are different and the circuit looks different, but you'll know how to solve these kind of problems if you look into this reference material. So I'll cover the reference material in next lecture, that is in Friday's lecture. But today we'll keep on continuing with whatever we were discussing before. That is the MOSFET cheat sheet, as well as learning why differential amplifiers are something that we need to learn next. Okay, so this reference material, what it tells you is that whenever you see a very complex circuit, you have to divide and conquer. That you divide the complex circuit into multiple stages, and you already know how these different stages work. You already know what is a common source stage. You already know what is a common gate stage. You already know what is a source follower. Now you just need to identify what different parts of the circuit does. For example, this first part of the circuit, again, it's a common gate stage, because your gate has a AC ground. Any DC bias means that it's an AC ground, right? There is no AC potential in a DC voltage. So gate is an AC ground, input is provided at the source terminal, output is taken from the gate. So again, the stage 1 is a common gate stage, and the output of the common gate stage goes to these two source followers, which are sort of connected in parallel, because the gates are connected together, the drains are connected together, and also the sources, which are both ground, are connected together. So it goes to two common source stages which are in parallel. And if you look into the homework problem, then the last stage of the homework problem is also very similar. That you have two common source stages which are connected, not in parallel though, because the gates are not connected together, but the drains and sources are connected together. So you can basically look into these reference material to understand how to solve the second problem in your homework number 6. Okay. So that's a little bit about the homework number 6 that's due next week. What we are going to do today is, we'll go over this MOSFET amplifier cheat, which will give you some use for any of your future courses, or later on whenever you need to refer to these different constructs or different circuits, such as common source amplifier, common gate amplifier, common drain amplifier, and so on. And this gives you an idea about how to analyze each part or each type of circuit that you might encounter later in the course or any other future course. So of course, common source is something that you have looked into before, that you have your input at the gate, you have your output at the drain, and your source is the common terminal or the reference terminal, and that's why it's called a common source. We have also looked into the small signal model of the common source, where the gate to source terminal is open. There is a GM/VGS amount of current flowing from drain to source. So this is your drain, this terminal is your source, and this terminal is your gate, right? Now, of course, here we are ignoring the RO, the effect of the output resistance of the transistor, and you already know that RO is equal to 1 upon lambda VDS. So if your lambda is given to be 0, or if you're asked to ignore lambda, the channel length modulation, then your RO is infinite, which means that the RO can be considered as an open circuit. But if there is a finite lambda, in that case, you have to consider this RO. But right now, just for simplicity, for the sake of simplicity, because in many times while doing the analysis of the circuit, you can ignore RO if RD is much, much smaller than RO, which will be the case in most practical circuits. That RO will be in the range of hundreds of kilo ohms, whereas RD will be in the range of kilo ohms, or maybe 10 kilo ohm or so, which is much, much smaller than RO. And you already know this from parallel combination of resistances, that if there are two resistances, one of them is much larger than the other, then the overall parallel resistance is similar to the smaller of the two. Okay, so clear the arrow right now. And okay, so the way to analyze any kind of MOSFET amplified circuit, or to find out the gain of any kind of MOSFET amplified circuit, it will be of the form this minus GM times R out. Okay, where GM is basically the it could also be plus GM times R out, depending on if you have a common drain structure or a source follower structure. But in case of the common source amplified, it's minus GM times R out, which means that there is an inversion in phase as compared to the input. So if your input looks like that, your output might look like this. It's an amplified version of the input, but there will be 180-degree phase difference. And why is that? That's because you consider the current flow from drain to source, and that is correct because for an NMOS amplifier or for an NMOS transistor, the current flows from drain to source. Electrons flow from source to drain, right? Electrons are the carriers which flow from source to drain, so the current will flow from drain to source. But since at the output side here, so for example, then in this loop, the current flows in this direction, but you are taking your output with a polarity that this is positive and this is negative. So as you see that the current flows in the opposite direction, and that is the reason why you have this negative sign for the common source case. For source follower or for common gate, you do not have this scenario that the current flows in the opposite direction of the output voltage, and that's why we say that the gain that you have for common gate or source followers will be positive, which just means that there will be no phase inversion as compared to the input side. Okay. Now, what if this is true, that okay, any kind of gain is a multiplication of a transconductance quantity and output resistance quantity. Again, we have proved this multiple times because transconductance is output current divided by input voltage. So if you represent GM as output current divided by input voltage, you have output current multiplied with output resistance quantity at the numerator, which means you have output voltage in the numerator divided by input voltage at the denominator. So that gives you voltage gain. Output voltage divided by input voltage, that's your voltage gain. So when, in this case, when your RO is infinite, when your RO is very, very large, and you are kind of ignoring the output resistance or of the transistor itself, in that case, your capital GM will be equal to small gm, your Rout will be equal to RT. If RO is not infinite, then capital GM will still be equal to small gm, and Rout will be equal to RO in parallel with RT. Now, what is the method to find capital GM? Again, it's very similar to what you do when you are trying to find out Thevenin equivalent or Norton equivalent circuits. Now, remember that when you are trying to find out GM, you are actually trying to find out the output current, and then you want to find out what is the ratio of the output current to the input voltage. That is your GM, right? Now, for any circuit, let's say you have a black box, you have to find out the output current, right? Would the current flow if the circuit stays open? No, right? So you have to short the output. So you have to short the RD, whatever is connected at the output or whatever is connected at the load. Remember that when you represent this circuit in this form, what is connected at the output as your load? That's your RD, right? The resistance is your load resistance in this case. So you have to short whatever is connected at the load. So initially RD was connected at the load, but you just short it. So you will not have any kind of load resistance present when you're trying to find out GM. And again, I'm not talking about anything new. It's just the same way that you find out a Norton equivalent current. This is not anything new. When you're trying to find out a Norton equivalent current, you remove the load, you short the load, the two terminals of the load, and you find out how much current is flowing through in this branch. Right? You find out that current which is flowing through in this branch as a function of the input voltage, and your GM will be I out divided by V, the output current divided by the input voltage in an AC term. So again, this is not anything new. This is the same method with which you find out Norton equivalent currents. The method to find R out, again, this is the same method as you find in Thevenin equivalent resistances. That if you have a black box and you want to find out what is the equivalent resistance looking into that black box from the output side. So you'll open the load first, right? You'll not connect any kind of load over here. Again, that's the method you use whenever you want to find out any Thevenin equivalent resistance. So it's the same method, nothing new. So you open the RD, you short the input voltage and kill any other independent voltage sources or even current. Right? So you don't connect anything at the input when you're trying to find out the output resistance. Again, the same method as you apply to find out the Thevenin equivalent resistance. Then you put a voltage source, a test voltage source Vx at the output, and find out how much current is going into the output terminal. Let's call that Ix. And the ratio of Vx over Ix will give you the output resistance in the no load condition. That when you do not have any kind of load connected, that's your output resistance. Now, the final Rout will basically be this output resistance that you see looking into this black box. And then if you connect a load over here, so let's say now after you have found out what is the output resistance of this black box, now if you connect a load resistance over here, then what would be the overall resistance looking into this terminal? That would be the resistance looking inside the black box in parallel with this resistance that you have connected as a load. So that would be your overall Rout. So now you'll put those values in this GM Rout formula. You already know how to find out your GM, capital GM. You know how to find out your capital Rout, and multiplication of those two will give you the voltage gain. So this is a generic. So this is again nothing new, but this is just a generic formula or a generic way to solve any kind of voltage gain or to find out the voltage gain in any kind of circuit. That you find out capital GM, the effective GM of the circuit. You find out Rout, which is the effective Rout of the circuit, and multiply that. That's how you'll find gain in any circuit. Right? So the method will be exactly same in solving any circuit that you encounter now, in future, or any other course. So if you look at an example with common source with source degeneration, again something we have solved before. What you want to find out is basically this AV, which is minus GM times Rout, right? Just writing the same equation as before. When Rho is infinitely large, in this, and again, I'm not solving the small signal model. At this point, I'm assuming that all of you should be able to solve the small signal model and find out the GM and Rout as you have done in the class in the previous lectures. Now I'm just summarizing what we have learned before. That is, your capital GM will be small gm divided by 1 plus GM Rs. Whenever you have this source degeneration, your GM reduces by a factor of 1 plus GM Rs. And of course, your output resistance, that is the output resistance looking at the output terminal, that will be equal to RT if your Rho is infinite. When Rho is not infinite, your GM, and this is something we have not solved in class, but if you take into consideration the Rho resistance that is connected between the drain and the source, and then if you just solve the KVL and KCL at those nodes, you'll see that your capital GM will look a little different than what we have seen before. So this is the exact formula when you try to consider Rho, but you don't need to remember this formula because usually in most circuit analysis, we ignore the Rho term. We assume that Rho is much higher. But in case you do not have an Rho which is much higher than all other resistances in the circuit, this is what your GM equation will eventually look like. And your Rout equation, so Rout is basically the resistance, basically looking into so let's say this is the final Rout at this point. So that's the resistance looking here, which will be a parallel combination of resistance looking into this side and the resistance that you see here, which is RD. So the parallel combination is clear, which is RD. But then there is also a resistance looking into this terminal or looking into the drain of the transistor. If the resistance is very high, if that resistance is infinitely large, then you just see an infinite resistance at this point. So whatever is in parallel with RD, that is infinite if Rho tends to infinity. And that's why in this case, we said that Rout is equal to RD because infinity in parallel with RD will be equal to RD. But if you don't consider that, and if we have solved this in maybe I think 2 lectures before, that if you are considering the effect of a finite Rho, the resistance that you see looking into the drain of a transistor, when nothing is connected at the source, you'll see a resistance of RO looking into the drain of the transistor. But in this case, you have a RS resistance connected at the source of the transistor. So the resistance looking into the drain, will be equal to, like in simpler terms, what I said is that, and this is something you can remember, that the intrinsic gain of the transistor is Dm times RO, right? So the resistance connected at the source will be multiplied with this Dm times RO, and then you can add an additional term RO to that, because RO is the resistance between drain to source of this transistor. So RO is the resistance looking between the drain and source of the transistor. But in series with that, you have an RS term. But that RS term sees an amplification looking into the drain of the transistor. And we have solved this 2 lectures before. So I'm not going to solve it again, but it's just that the resistance looking into the drain of the transistor when there is a RS resistance connected at the source will be equal to Gm times RO times RS plus RO. So that's just, like, again, this is an approximation. The exact form is something that we had solved before, which is RO plus 1 plus Gm RO times RS. So instead of 1 plus Gm RO, I just assume that we can approximate it to be Gm times RO. Right? So if Gm times RO is 50, 1 plus Gm times RO is 51. So it doesn't really make much of a difference in terms of the value. So the R out looking into the drain of the transistor when there is a resistance connected at the source will be the intrinsic gain of the transistor multiplied with the resistance connected at the source plus RO. Now, of course, if RO is infinite, you do not need to consider any of that, and Gm times RO times RS plus RO will be equal to infinite. So it doesn't matter if RO is infinite. But if RO is finite, this is the equation that you'll end up with. All right, so this is what I'm summarizing over here again, that looking into the drain of the transistor, you'll see RO if RO is infinite. If RO is not infinite, you'll see RO plus 1 plus Gm RO times RS. The proof is there, I think 2 lectures back in Friday's lecture, if you want to go over the proof of this equation once again. Or it is also provided over here, I guess. Let's see. Okay, so if you have a common source stage with source degeneration, how to find out the Gm? So for example, we said that Gm will be this equation when you are considering a finite RO, right? When your RO is not infinite. So the proof is provided once again over here, just so that you don't need to go back to the previous lecture once again. So I'm not going through the analysis of the derivation once again. It's just a 2 to 3 line derivation. Please go over it at your own pace. But this is what Gm will look like if you have a finite RO. And degeneration also causes increase in the output resistance. This is also again something that we have seen, that the output resistance will be RO plus 1 plus Gm RO times RS. So it is increased by an amount of 1 plus Gm RO times RS as compared to what it was before. It was only RO before, but now as you are connected to RS resistance at the source, the output resistance increases. Again, something that we have proved, and this is what you can again go over the proof. We have done that before, but it's just that I wanted to keep everything at the same place so that you do not need to go to any other lecture to understand why Gm and RO is in this form as you have a source degeneration. All right. Now, for common drain or a source follower, you'll apply your input at the gate, you'll take your output at the source, and the gain will be almost equal to 1. This is what we have learned before. And the exact value of the gain will be GMRS divided by 1 plus GMRS. Again, that is something we have proved before from the small signal model. Now, in this case, again, your gain, voltage gain will be capital Gm times R out. Remember that in this case, the current flows from drain to source. And the way this V out is considered, this is the positive terminal and this is the negative terminal for the V out, right? So the V out is aligned with the direction of the current. And that's the reason why you do not have the negative sign anymore. You have a V as a positive Gm times R out, because the direction of the current aligns with the way you are taking the polarities of the output voltage. Now again, when RO is infinite, your capital Gm is equal to small gm, and R out, that is the resistance looking into the output terminal, that would be RS. So this is your output terminal, right? At the output terminal looking down, you'll see this resistance RS. And at the output terminal looking up, you'll see a resistance of 1 upon Gm. Because looking into the source of a transistor, you'll see a resistance of 1 upon Gm. Again, something that we have proved before, so I'm not going to do that again. Questions?
If you had a second resistor above the drain,
Right.
would the output be 1 over Gm in series with that resistance, all in parallel with?
That's a great question. So if you have, so in that case, I would recommend that you solve the small signal model. But what you will see eventually is that if you have let's say our RD resistance, actually I am showing it over here, that if you have a RD resistance connected here, then the resistance that you see is basically RO coming from the drain to source resistance of the transistor. And because you know that resistance is basically a bidirectional quantity, so something that, so if you look at the resistance from the left hand side and the value of that resistance is 1 kilo ohm, if you look at the resistance from the right hand side, it will still remain 1 kilo ohm, right? So the drain to source resistance of the transistor still remains R. And what, as you said, that the RD comes in series with that. So you have RO plus RD, that's in your numerator. But you divide everything by 1 plus Gm RO. That's because as you are looking from the drain, and you'll see this as you solve the small signal model. So that's kind of like a homework exercise for you guys. That as you're looking into the drain of the transistor and you have a RD transistor connected at the drain, what would be the overall resistance looking into the source terminal? So you'll see that it will be RO plus RD, that's the resistance connected between drain and source, and the resistance connected above at the drain terminal. But everything will be divided by 1 plus GMR. So it's as if, as you are looking from the source, everything gets divided by 1 plus GMR. As you look from the drain, everything gets multiplied by 1 plus GMR. So if you go back here, as you are looking from the drain, the RS, that gets multiplied by 1 plus GMR. Okay? So that's what, if you solve the small signal model, you'll see the proof. And I'm again assuming that at this point you can solve the small signal models to come up with these equations yourselves. So if you look from the drain, the resistance that is connected at the source gets multiplied with 1 plus GMR factor. As you are looking from the source, the resistance connected at the drain, that gets divided by this 1 plus GMR factor. And again, of course, if you assume your RO is infinitely large, this equation will become 1 upon Gm, because here RO is at the numerator and denominator. You just divide the numerator and denominator with RO. You'll get 1 plus RD divided by RO. And if RO is infinite, then RD divided by RO will be 0. So you get 1 in the numerator. And in the denominator, you have Gm plus 1 upon RO. Again, if RO is infinitely large, you just get Gm. So this equation becomes that equation if RO is infinitely large. But then again, for example, in this course, there would be hardly any cases where you have to consider a finite RO. Because this is an undergraduate course, we generally do not make things that complex, right? We'll consider that RO is infinitely large in all cases in your, let's say, in your exam or any other complex problem. We'll not consider, but if you had to consider the effect of RO, this is the equation you would have had to use. Right? So I just wanted to make sure that you know that there is an effect of the finite RO for the transistor, even though these kind of problems will not be there in your exams. In your exams, you can consider your RO to be infinitely large. And that will make life simpler, that your resistance looking into the source will just be 1 upon Gm, and not this complex quantity, or not this like quantity of RO plus RD divided by 1 plus Gm. Okay. Similarly for this case, that as you are looking into the drain of the transistor, you can say that you are seeing RO, which is an infinitely large resistance. But if you had to consider a finite RO, this is what you'll end up with. And again, the proof is you just have to solve the small signal model. All right. Common gate, again, something that we have seen before. Everything is same as common source. And if you have a degeneration resistance, then you can also have the source degeneration, except for the sign. So common gate, the input is applied at the source, the gate is grounded, and the output is taken at the drain. Why am I saying that everything is same as common source with source regeneration except for the sign? That's because you can think of it in this way, that for common source configuration, you applied your input at the gate and you let your source be the common terminal. Here you are applying your input at the source and you're letting your gate be the common terminal. So in this case, so in common source case, whatever VGS you are applying, that becomes VSG for a common gate configuration, right? So if you have the same input voltage, let's say 10 millivolt of input voltage, you are applying VGS of 10 millivolt in case of common source, but for common gate, that becomes a VSG of 10 millivolt. But the transistor equations, everything remains same. For the transistor, the equation of I out is basically GM times VGS. Right? So if your VGS is now equal to minus 10 millivolt because you have a 10 millivolt at your source and a 0 millivolt at your gate. So you have a negative sign. And that's why I'm saying that everything will be same except for the sign. So VGS, so gate to source voltage is minus of source to gate voltage. And that's the reason everything is same except for the sign. You can consider this as the same scenario as having a common source stage, but having a negative Vin applied at the source. And by negative, I do not mean an absolute negative value, it's just that the phase is reversed. Okay. Diode connected MOSFETs, again, something that we have seen before, that if you connect your gate and drain together, this is called a diode connected configuration. Why is it called a diode connected configuration? Again, that's because in a diode, what do you expect? You expect the current to flow in one direction. But you don't expect the current to flow in the other direction. So this direction, current cannot flow. In this case, as you have connected the gate and drain together, now what is the definition of the drain for an NMOS transistor? The definition of the drain is that whatever terminal is at a higher potential, because you know that the current will always flow from drain to source for an NMOS. So whatever terminal is at a higher potential becomes the drain. Right? So if you think about the structure of the NMOS, so it's symmetric, right? So there is no difference between the source and the drain. We just call this left-hand side terminal as source and right-hand side terminal as the drain. But then there's no hard and fast rule that this left-hand side terminal has to be the source. The right-hand side terminal can also be the source, and this can be the drain. It depends on which terminal has the higher potential. If this terminal has the higher potential, this will become drain and the current will flow in this direction. If this terminal has the higher potential, then that will become the drain and current will flow in this direction. So for any transistor, the drain and source terminals are reversible. You can, whatever terminal, wherever you have the higher potential for an NMOS transistor, that becomes the drain. For PMOS, it will be the reverse. For PMOS, whichever terminal has the higher potential, that will become the source. Because for PMOS, current flows from source to drain. And you always know that current flows from a higher potential to lower potential. That's an absolute truth. Current will always flow from higher potential to lower potential. You cannot reverse that. So if current flows from higher potential to lower potential, and if for the NMOS the current flows from drain to source, then you know that the drain terminal will always be at a higher potential than the source. Okay. So this is how we are defining the drain, and then we are connecting the drain to the gate terminal. Now, what if you reverse the polarity of the voltages? So, for example, for a diode, if this is positive and this is negative, the current will flow in this direction. But if this is positive and this is negative, the current will not flow in the direction. The diode will stop the current flow from the positive terminal to the negative, from the positive voltage to the negative voltage, because the diode will become reverse biased. Right? So now if you draw an analogy to that concept over here, that let's say I just connect my positive voltage over here and negative voltage over here. Right? Instead of connecting this to ground, let's connect it to a positive voltage and let's connect this to a negative voltage. Now, because current always flows from positive voltage to negative terminal or positive potential to negative potential, and you define your drain and source terminals as follows, that the drain terminal is always the terminal with the higher potential. So in that case, this will become the drain terminal, right? And this will actually become the source terminal. So you'll have to change the symbol of the transistor, because then the current is trying to flow in this direction. But as this becomes the source terminal, and this is the gate, what do you have? You have your gate and source connected together. If gate and source are connected together, your VGS is equal to 0. If VGS is equal to 0, the MOSFET is off. If the MOSFET is off, there cannot be any current flow through the MOSFET. And that is why it is called a diode connected MOSFET. That it will let current flow in only one direction, and it will not let the current flow in the other direction. Because in the other direction, your VGS becomes 0. And if VGS becomes 0, the transistor becomes off, and there cannot be any current flow. So this could be a little tricky to understand at first, but think about it, it will become very clear that why is it called diode connected? Because diodes let current flow in only one direction, and this is what you are doing here. That only if this is a positive terminal and this is a negative terminal, current will flow. If this becomes a positive terminal and this becomes a negative terminal, current will not flow. Now, for a diode connected MOSFET, again, you can do an analysis of let's say a small signal analysis again. So what do you have here? You have your gate and drain connected together. So VGS is equal to your VDS. So this is your gate terminal, this is your drain terminal, and this is your source terminal. This connection between gate and drain is basically that connection. So so that we don't have any confusion, let me remove this. And this is your drain terminal, this is your source terminal. Drain terminal is positive and the source terminal is negative. And gate and drain are connected together. You have GM times VDS connected at the drain terminal as this current. You have RO, let's say you have some amount of RO over here. And what you're trying to do is that you're trying to find out what is the resistance looking into the drain terminal when you have the diode connected MOSFET. Now, this is a special case. Till now, what we have learned is that as you're looking into the drain of the transistor, you'll see a resistance of RO. This is why we are learning this diode connected MOSFET, because this is the only scenario where you will not see a RO resistance looking into the drain of the transistor. This is the only scenario that we'll encounter where the resistance looking into the drain will not be equal to RO. It will actually be equal to 1 upon GM, and we'll solve it through the small signal model. So again, as you know that how to solve the RO of a system or a circuit is that you disconnect the load, you connect a test voltage source Vx at the output side, and you measure what is the current flowing into the output terminal or the terminal of interest, and the ratio of Vx over Ix will give you the output resistance. Right? Again, the same method. Now here, your gate to source voltage VGS is actually equal to your Vx, because see, your gate is connected to the drain, and drain is the output terminal where you're connecting this Vx voltage. So whatever Vx you have is equal to your VGS. Now you can write your Ix, the current that is going inside this op-amp, inside the transistor, equal to the value. So that current that goes in, that gets divided into two branches. One that flows through the GM-VGS, so the current is equal to GM-VGS, and the other one flows through this branch through the RO resistance. So Ix will be equal to GM-VGS plus Vx divided by RO. So GM-VGS plus Vx divided by RO. So you have GM times Vx plus Vx divided by RO. Now you have an equation where you have only Ix and Vx. So you can find out what is Ix divided by Vx or Vx divided by Ix, in whatever form you want to find it out. And you'll see your Vx divided by Ix will be RO divided by 1 plus GM-RO. And if RO is very high, this reduces to 1 upon GM. So this is the only scenario when you are looking into the drain of the transistor, but you do not see a resistance of RO. Instead, you see 1 upon GM. So if you ask me what do I remember from, or what do I conclude from all these discussions, it's just that it's three things. One, that if you are looking into the drain of a transistor, which is not direct connected, you will see RO. If you look into the source of the transistor, you will see 1 upon GM. That's the resistance you will see. And if the transistor is direct connected, then looking at the drain of the transistor again, you will not see RO. Instead, you will again see 1 upon GM. Okay. So if you remember these three things, you can solve any problem related to these different concepts. Okay. So only if the transistor is direct connected, you'll see 1 upon GM looking into the drain. Looking into the source, of course, you'll always see 1 upon GM. And if the transistor is not direct connected, you'll see RO looking into the drain of the transistor. So three things, if you remember, you should be able to solve any problem in the homeworks or in the exams. All right. So this is just again the output impedance for the common gate stage. Now for the common gate stage, your output is taken from the drain terminal. So ideally you should see RO resistance, but this is again the proof of the scenario when you have a finite RO and looking into the drain at the output. So for a common gate stage, the input is provided at the source, the output is taken at the drain, and the gate terminal is an AC ground. So if you think about the output impedance for a common gate stage, we already know, or we already have some idea about it. That would be almost equal to this RO plus 1 plus GM RO times RS. Okay, if you have a RS resistance connected at the source. So this will be very similar to the analysis that we have done before. And this is just a proof of that. All right. Input impedance for the common gate state. Again, as you are looking into the source of a transistor, the input impedance will be almost equal to 1 upon GM. And what this, you'll see that in these slides, it will be a little more involved, it will be a little more complex than this 1 upon GM output that you're getting, or the final Vx over Ix, or the input impedance that you are seeing is actually not 1 upon GM, but you have these other terms as well. And they come in because you're considering these non-idealities of RO. And there is also another non-ideality, which is called the body bias non-ideality. So for example, what is the body bias non-ideality? Is that for an NMOS, till now we have always said that the body of the NMOS, let's say this is your source, this is your drain, this is your gate. We said that body of the NMOS we are always grounding. Why is that? Because the source is also ground, and you do not want to forward bias this source to bulk diode. If you do not want to forward bias the source to bulk diode, you would want to put the bulk to a lower potential, and the drain is all at a higher potential. So this is at VDS. So this drain to bulk diode is reverse bias. The source to bulk diode is also having no bias because your bulk is grounded and the source is also grounded. But if you had this bulk connected to a small voltage, for example, let's say 0.1 volt or 0.2 volt, there is a possibility that this source to bulk or drain to bulk diodes will become forward bias. And that will have some amount of current flowing through the device, and that is represented as this GMB, and it will be a function of the bulk to source voltage. So GMB times VBS. So again, this is a non-ideality. You do not need to consider it right now, but in any kind of graduate classes, this is again something that becomes very important. So right now, you do not need to consider it, but and you can say that your resistance looking into the source of the transistor is still 1 upon GM, but this is again giving you a glimpse of all the different non-idealities that are present in the system. That becomes important when you are trying to make your analysis more and more accurate. So in graduate classes, you need to make your analysis more accurate, and that's why you have to take RO and the effect of GMB VBS into consideration. But for an undergraduate class, we are not considering it right now. But this is just so that you know that these kind of non-idealities do exist. All right. So if you look into a few more examples, like let's try to focus on a few more examples in the rest of the 4 minutes that you have in today's class. So let's say you have a common source amplifier. So this is your common source. You're applying your input at the gate. Your source is grounded and your output is taken at the drain terminal. But for this common source amplifier, instead of connecting a resistance at the drain as a load, what you're doing here is that you have a diode connected MOSFET. So this is the PMOS. PMOS means this is the source terminal, this is the drain terminal. You're connecting the drain and gate together, so that becomes a diode connected MOSFET. So you're having a diode connected load instead of having a resistive load. And you know that for a diode connected MOSFET, looking into the drain of the MOSFET, you'll see 1/Gm. That's the resistance. Instead of having a resistance of RD connected at the drain of this M1 transistor, you're connecting a resistance of 1/Gm that comes from the M2 transistor. So the analysis will still be same. You do not need to consider two different transistors. You can just divide and conquer. So that's something you always need to do for any kind of circuit that you see. That here you see you identify that this is a common source, right? I guess at this point all of you can identify that this is a common source. And if that is a common source, what is the load connected to that common source stage? The load connected to the common source stage is the resistance looking into the drain of a diode connected MOSFET. And we have proved that for a diode connected MOSFET, the resistance looking into the drain is equal to 1/Gm. So again, you already know that this equation will be Gm times RD, and your RD is basically, let's call it Gm1 times RD in this case, and you know your RD, the resistance connected at the drain, is 1/Gm2. That's for the N2 transistor. So this will be equal to minus of Gm1 divided by Gm2. Okay? So that will be your gain for this scenario. And now you can represent your Gm as square root of twice K times ID. So you'll have square root of twice K1 times ID1 divided by square root of twice K2 times ID2. That gives you minus of square root K1 over K2. Now remember that K is equal to mu times Ux times W over L. So K1 is mu n times Ux times W over L1. K2 is mu P times Ux times W over L2. Because M2 is a PMOS transistor, M1 is a NMOS transistor. Now, usually mu n is equal to 2 times mu P. The mobility of a NMOS transistor is usually 2 times higher than the mobility of a PMOS transistor. And that is just because electrons are faster than holes. Now, if that is true, then your AV, that becomes minus of square root times square root of omega over L of 1 divided by omega over L of 2. And if your L's lengths are equal, then this just becomes minus of square root 2 times square root of omega 1 or W1 over W2. Yeah. So W is the width of the MOSFET. So width of the M1 MOSFET divided by width of the M2 MOSFET, taking a square root of that and multiplying it with the square root of 2, that will give you the theoretical gain of this system. And of course, for two transistors, you cannot have a very high ratio of width. So for example, if one transistor is, let's say as big as this phone, the other transistor cannot be as big as this room, right? So it becomes very hard to connect the two transistors if the ratio of widths are very different. So W1 over W2, that ratio, let's say even if that ratio is 100, the gain that you get is square root of 100 times square root of 2. So you get a gain of, let's say, about 14 or so. And having a ratio of 100 is very difficult in an actual scenario, that you have a transistor which is 100 times bigger than the other transistor. That generally does not happen. Or it becomes much difficult to connect the different terminals of the transistors just because of space limitations if one transistor is larger than the other transistor by 100 times. So let's say that one transistor is 25 times larger than the other one, then square root of 25 will give you a gain of 5. So usually diode connected load, which diode connected load, the gain that you can have is in the range of 5 or 7 or so. So we'll stop here and we'll look at other scenarios, how you can improve the gain of this kind of a MOSFET based structure, and will not have a diode connected load, we'll have something called a current source load. And that is something we'll take a look at in the next lecture.